Hello everybody, myself Jyoti and this is 8th lecture on Raman spectra, and today we are going to discuss Raman spectrometer. This is how the Raman spectrometer looks like. You can see this C, it is a glass tube which is called as Raman tube or Raman cell. It is surrounded by a water jacket. This water jacket, through this water jacket we pass cold water so as to prevent the glass tube from overheating. Then you can see there is one horn shape over here, and why it is horn shaped at this particular point, that I will tell you later. Here there is a mercury arc, and this mercury arc is used to heat the sample. Then we have slits S1, S2 and L which are placed over there so that the scattered radiation can be collimated, and it is then later on made to fall on a slit. You can see here it is a slit of the spectrograph, so it is made to fall on the slit of the spectrograph. Now, Raman observed the scattered light by a liquid sample by using a spectrometer which was placed at right angles to the incident light. And the conventional experimental setup to study Raman effect was developed by Robert William Wood, and the sample free-form bubbles and dust was contained in a glass tube C called as Raman tube or Raman cell. And this Raman tube or Raman cell, it is 2 to 3 centimeter in diameter and 20 to 30 centimeter in length. And this tube was closed at one end by an optically plain glass tube which served as a window for the scattered radiation. Here you can see this is the window for the scattered radiation, and the other portion, it is horn shape, and this horn shape portion, it is blackened. It is blackened from outside to avoid multiple reflections and to provide suitable background. How the spectrometer basically works. The light from a mercury arc source was first passed through a filter to isolate a suitable monochromatic radiation which was then incident on the sample. One of the requirement for a Raman spectrometer is the light which we will be using, it should be highly monochromatic in nature, and that is how after the source we put a filter so that the source of light will be highly monochromatic in nature. And the number of reflectors were suitably arranged around the tube so as to direct much of the incident light into the sample, and so there is no loss of any radiation. The tube was protected from overheating by liquid due to proximity of the exciting arc by circulating cold water. That is why there was a water jacket. And slits S1 and S2 align the scattered radiation along the axis of the Raman tube, and the lens L, it focuses the scattered radiation on the slit of the spectrograph which we use to analyze the spectrum. So this is how the working is. And the spectrograph, it is carefully aligned along the axis of the tube and screened from the direct rays from the source, and spectrograph had large aperture and high resolving power. So this is all about how the Raman spectrometer is constructed, how it's the arrangement and how it works. Now when we get the Raman spectrum, this Raman spectrum is very weak in nature. Why it is so? Raman spectrum is weak spectrum because Raman effect is comprised of a very small fraction of the incident photon. What does this mean? When we have studied Raman effect, we know that Raman effect is the one where when the light is incident on a sample, the scattered radiation, it consists of three frequencies. One frequency which will be having frequency same as that of the incident radiation, and other two slightly higher and slightly lesser, which gives rise to your Stokes line and anti-Stokes line. And we have one unperturbed line. Unperturbed line, it is because of the Rayleigh scattering or elastic scattering, and we get Stokes line and anti-Stokes line because of the inelastic scattering. Now the probability for the photon to have inelastic scattering, it is very less. 1 out of 10 raised to 7 photons will have will show the change in frequency. So you can imagine that how weak the spectrum is, and as a result it requires a long interaction time to collect enough photons to measure a detectable signal. And the original spectrometer which was used earlier, it needed exposure time of the order of 50 to 100 hours. Now the modern spectrometers, they are designed in such a way that the exposure time has quite reduced now. So, to overcome this difficulty, very long sample tubes and very intense extended sources were used in those days. And though it helped to reduce the exposure time, to some extent it posed some other problems. It required considerable amount of sample. And we know that being a researcher, you know that the amount of sample which can be used for a particular characterization, generally we have a small amount of sample. So that was the problem. The extended source allowed a good deal of exciting radiation to be scattered directly into the spectrometer, where it masked all the Raman lines less than some 100 per centimeter. So when we have the modern version of Raman spectrometer, since mercury arc sources they are not intense enough, now we the preferred source for the Raman spectroscopy, it is laser. So nowadays in the modern spectrometer we use laser sources because we know that the property of laser is it is highly monochromatic in nature. And now the lasers which are available in the market, they are not they are uh, easily available, and they are relatively inexpensive, so preferred choice is laser. The laser is almost ideal for Raman spectrometer because it gives a very narrow, highly monochromatic and coherent beam which can be focused very finely into a small sample. And here the sample which will be required, it is also less, and the exposure time is also reduced. And nowadays in modern spectrometers you can get the spectra just in few minutes. So earlier we need to have the exposure time of the order of 50 to 100 hours, and now in few minutes you can get the Raman spectra. So that is all about the Raman spectrometer. Thank you so much.